Let's remind ourselves of the second order differential equation which we wrote for mass on a spring. So the second order differential equation for mass on a spring can be written as second derivative of x with respect to time plus c over m dx dt plus k over m x equals to 1 over m ft, and we rewrote it as d square x dt square plus 2 times the damping ratio times the natural frequency times dx dt plus square of the natural frequency times x equals to function of time. And then we imagined three possibilities resulting into three different types of motion. So possibility number one was if c over 2m is greater than square root of k over m, then we get x as a function of time equals to c1e raised to the power minus c over 2m plus square root of c over 2m square minus k over m t plus c2 e raised to the power negative c over 2m minus square root of c over 2m square minus k over m multiplied by t, and we said this results into overdamped exponentially decaying motion. Okay, overdamped exponentially decaying motion. So in this case, there are no oscillations because there are no sinusoidal terms in the expression which represents the solution for x. So let's first try to see the damping ratio in this equation, inequality. So if you compare the coefficient of dx dt in the first version of the differential equation with the second version, and as we have already shown in the previous clip, we can write c over 2m is equal to zeta times omega n. And we know k over m is equals to the square of the natural frequency. So square root of k over m is equal to natural frequency. So c over 2m greater than square root of k over m is equivalent to zeta times omega n is greater than omega n. So this means zeta is greater than 1. So we can say that when the damping ratio is greater than 1, we get overdamped exponentially decaying motion. So all this discussion assumes that c is positive, because only when c is positive the exponential function will decay. But what if c is negative? So only the sign is different. When c is negative, this condition c divided by 2m is greater than square root of k over m will flip, and instead of c we will get a negative c. So you can convince yourself of this if you again go back to the equation for the eigenvalues of the system, of the oscillating system, and then you will realize this to be the case. Also note that here in this particular solution for x, c being a positive or negative does not really make any difference to the term under the square root. It only affects c divided by 2m. So if c is positive, then minus c divided by 2m leads to decay, exponential decay. But if c is negative, then negative, negative, positive, we will get e raised to the power something positive times t. So this will lead to an exponentially growing function. So when c is negative, the statement is negative c divided by 2m is greater than square root of k over m, and this means negative times damping ratio omega n is greater than omega n, or negative of damping ratio is greater than 1, or damping ratio is less than negative 1. So when damping ratio is less than negative 1, we can say that we get an overdamped exponentially growing motion. Okay, so this leads to overdamped exponentially growing motion, which means the motion will now not be stable. It will not come back to the equilibrium. It will keep moving away and away from equilibrium. So okay, so far we obtained two physical interpretations of the damping ratio. If damping ratio is greater than 1, then we get an overdamped exponentially decaying motion. If damping ratio is less than negative 1, then we get overdamped exponentially growing motion. Now let's revisit the other solution for x that we had previously obtained. The other solution was for the case c over tm to m equals to square root of k divided by m. Now in this case, x as a function of time is equal to c1 plus c2 t e to the power lambda t, where lambda is equals to minus c over 2m. So first of all, let's see how this relation can be written in terms of the damping ratio. So we can write this as damping ratio times the natural frequency is equal to the natural frequency. So this is damping ratio equals to 1. So when damping ratio equals to 1, what was the physical interpretation based on this equation? So obviously lambda is now negative, so we should expect an exponentially decaying motion, and we call this a critically damped motion. Okay, so we call this a critically damped motion. Now this is assuming that c is positive. If c is negative, then what will happen? If c is negative, then this statement will become negative times the damping ratio omega n equals to omega n. So we get damping ratio equals to negative 1. And at the same time, a negative c means lambda will be positive, which means we will get a growing motion. So when zeta equals to negative 1, we will get critically damped exponentially growing motion. So to put the zeta equals to 1 in the same way, we can say that this is critically damped exponentially decaying motion. Actually, decaying motion. Now let's analyze the third case. So in the third case, we had c over 2m is less than square root of k over m. Again, let's write this in terms of zeta and omega n. So this gives zeta is less than 1. And in this condition, the solution was sinusoidal, and x as a function of time was e to the power negative c over 2m t, a cosine of square root of k over m minus c over 2m square t plus b sine square root of k over m minus c over 2m square t. And when c is positive, because of this exponential term, there will be decay, and because of sine and cosine, there will be a sinusoidal motion, which is the oscillation. Now, when I say zeta is less than 1, this less than 1 range can be now separated into two sub-ranges. So one could be zeta is between 1 and 0. So basically zeta is positive, and other is zeta is between negative 1 and 0. So that is zeta negative. It is important to make this distinction because zeta being positive implies that c is positive. Zeta being negative implies that c is negative, and this will have opposite effects on the solution of x. Like for example, when zeta is positive, that is c is positive, we will get exponential decay. When zeta is negative, then this c will be negative, so we will have e raised to the power something positive times t, so which will lead to exponential growth. Okay. Now, I did not discuss zeta less than negative 1 here because that has already been covered. That leads to overdamped exponentially growing motion. Okay. All right. So when zeta is between 0 and 1, yes, we get overdamped we get underdamped exponentially decaying sinusoidal motion. But when zeta is between negative 1 and 0, we get underdamped exponentially growing sinusoidal motion. So in this way, depending on the value of zeta, the oscillating system may show different type of behavior. Now let us summarize our results in one table.